Hello everyone, my name is Bigtran and in this video I will be presenting about the validation of reference evapotranspiration RET and actual evapotranspiration and interception AETI data layers of WaPOR. We will revisit the definition of RET and AETI. Based on these definitions, we can identify the data that can be used as reference for the validation of these two data layers. We will discuss validation steps including evaluating reference data. At the end of this video, I will give some examples of AETI validation, and you can work on an exercise to validate the AETI data layers from WaPOR version 2 data. Before validating the data layer, we need to define what estimates the data layer provides. The WaPOR catalog provides definitions of RET and AETI data layers as follows. Reference evapotranspiration (RET) is defined as the evapotranspiration from a hypothetical reference crop, and it simulates the behavior of a well-watered grass surface. Notice that RET is different from potential evapotranspiration, which it was defined by Penman in 1948. The crop in PET definition is not specifically defined, while in RET definition, the reference crop is well defined as a crop with an assumed crop height of 0.12 meters, a fixed surface resistance of 70 seconds per meter, and an albedo of 0.23. The actual evapotranspiration and interception (AETI) is defined as the sum of the soil evaporation, canopy transpiration, and evaporation from rainfall intercepted by leaves. Due to the definition of RET, there are limited observations that can be used as a reference for validation. We can only validate RET with the actual measurements of ET over a surface that has the same characteristics as the hypothetical reference crop. Alternatively, we can calculate RET from ground-based measurements using the same method, the FAO56 method, then compare ground-based RET with the WaPOR RET layers. The data requirements for FAO56 method are often fulfilled by standard weather stations, including air temperature, humidity, radiation, and wind speed. For the validation of AETI, there are many methods to estimate AETI at the field scale. For example, eddy covariance, lysimeters, Bowen ratio energy balance systems. Each reference method is based on a different principles and covers a different surface area. For validation of AETI components, evaporation pans can be used to validate the evaporation component, while sap flow measurements can be used to validate the transpiration component. For more information about each method, please see the reading material. At the river basin scale, we can apply the residual of water balance to validate the basin scale AETI when other variables are known. This method is applicable to annual or sometimes monthly time steps. For example, precipitation can be derived from remote sensing or field measurements. Discharge can be measured, and the change in water storage can be derived from Gray's dataset or assumed to be zero for a long period. There are several public data sources that provide actual evapotranspiration in situ data. For example, the FluxNet is a global network of eddy covariance towers that provide access to long-term ETA data for over 500 sites. However, in regions where there is a lack of eddy covariance measurements, the more common reference for validation of remote sensing derived ET is using basin water balance, Bowen ratio energy balance system, and the FAO 56 method for crop evapotranspiration. Before validating RET and AETI data layers, we need to evaluate the reference data. Firstly, the accuracy of reference data needs to be assessed. This means estimating errors in measurements or water balance components and flagging measurements that are not reliable for validation. Secondly, it's important that both remote sensing derived data and reference data cover the same temporal and spatial range, and they are resampled to the same spatial and temporal scale. For this, metadata on the spatial and temporal scale of the measurement is needed. In case there is no reliable reference data, other approaches than validation can be used to assess the quality of the data layers. For example, comparing with other remote sensing-based RET or AETI data products, evaluating input data from RET and AETI models, or evaluating the physical plausibility, for example, correlation with other related variables. A more computationally demanding approach is to conduct sensitivity and uncertainty analysis of the model that produce RET and AETI datasets. For this, access to the source code of the model is needed. However, we will not discuss in detail all these approaches but focus on validation. Here are some examples of WaPOR AETI validation. Several performance metrics should be calculated to characterize the accuracy and precision of the data. The most common metrics are root mean squared error, bias, correlation coefficient, and coefficient of determination. Bias and mean absolute percentage error can be used to evaluate systematic error. Root mean square error includes random error, and correlation coefficient shows the linear relationship between remote sensing data and reference data. Here, WaPOR version 2 AETI datasets are shown to have strong linear relationship with water balance derived AET at the reverse basin scale, as shown by R and R square. However, the bias is quite high and increases with increasing AETI. The same plot and metrics for validation against 14 eddy covariance locations show that correlation is lower and error is higher at the daily and field scale. It is important to validate at each site individually to determine where and when the data layers are more accurate. For this purpose, time series plots for both remote sensing data and reference data can be used. Here, the time series plots show that WaPOR version 2 AETI underestimate ET in rain-fed crops when ET is high. Meanwhile, it overestimates ET in irrigated crops. Keep in mind that the accuracy of the remote sensing dataset might be different across climate zones, land cover, and other conditions. In the next exercise, you will validate WaPOR AETI using eddy covariance dataset